In this video, we're continuing our discussion on the principal axis of transformation as we began in video number 33. And again, to remind you, we're really drawing heavily now upon what we did in some of the previous videos, particularly videos 17 and 18, when we diagonalized matrices. Video number 26, we first discussed similar matrices. Also, video number 25, we talked about eigenvectors of symmetric matrices and the fact that for a symmetric matrix, its eigenvectors are orthogonal. And then in videos 27 through 31 is when we start to deal with orthogonal matrices. The playlist for all the videos is at the website digital-university.org. Now, what we're going to do here is exactly the same what we just did in video number 33, except here, in this particular case, the primed axes are perpendicular to one another. So we can think of the primed axis as just the xy coordinate axis being tilted. And again, we're saying that if we have a matrix that transforms vector small r into vector large R, we call it matrix P. And again, we started having these types of discussions in video number 27, so that if I know this is in the xy system now, so if we know an xy point on vector R, then we can determine the corresponding xy point on large vector R via matrix P. Then here we have a matrix that takes an x prime, y prime point and tells us the corresponding xy point. So if we know, for example, on vector R, we know an x prime, y prime coordinates, then matrix C will tell us its corresponding xy coordinates. And of course, that same matrix will do the same trick for this vector. If we know here a particular x prime, y prime point, by using matrix C, we can determine its corresponding xy point. What we don't know how to do right now is this. If we have, say, on small vector R, an x prime, y prime point, how do we determine the corresponding xy, y prime point in big vector R? So if we have some point here on small vector R and we know its x prime, y prime coordinates, now we're saying for the corresponding point on this vector, what would be those x prime, y prime coordinates? We don't know how to do that, but again, proceeding exactly as we did in video number 33, we can find out soon enough. We have here this equation, only R, that's here is R expressed in terms of R prime, so we have C R prime equals matrix P times small r, but that's this. And again, both matrix P and matrix C, these have to be non-singular matrices. They have to have unique solutions. Otherwise, you wouldn't have any one-to-one correspondence. So here, we can multiply both sides by the inverse of C, and we will get just as you saw us do in the last video, we get this expression. So again, this tells us if we know an x prime, y prime point on vector small r, multiplying these three matrices together gives us a matrix that tells us the corresponding x prime, y prime point on vector large R. And this is what is called a similar matrix. So this is what we did, exactly the same thing in the previous video. Now here, the difference is because these x prime, y primes are perpendicular, or essentially we can think of them as just tilting the xy coordinate axis. What we did, I think it was in video number 28, we determined what the matrix C is. This takes x prime, y prime, and gives xy, and here's the matrix that does it. So for this particular case then, when we're dealing with, when our primed axes are perpendicular, and assuming we know the angle here, then we know what the matrix C is going to be. Well, okay, that we wanted to establish. Now, let's take it a step further. Suppose that for matrix P, and matrix P again is what transforms vector R into vector large R, knowing their xy coordinates. So if I'm on here, I know the xy and small r, then by using matrix P I can determine the corresponding xy on large R. Suppose that besides being non-singular though, suppose that P is a symmetric matrix. Let's just say in general, let's say it has components, say, A, B, B, C. Here are the components in a general form of a matrix P, 2 by 2. We're just in two-dimensional space here. So this is symmetrical. If we take its transpose, it just gives us matrix P back again. What do we know, though, about symmetric matrices? Well, its two eigenvectors are orthogonal. That's characteristic of symmetric matrices. I think it was in video number 25 when we actually proved that. So if we have a symmetrical matrix P with two orthogonal eigenvectors, vector x1 orthogonal vector x2, then its eigenvectors might be able to serve as the x prime, y prime axis. So let's pursue that and see where this line of thought takes us to. So we're saying that we have a matrix P, a symmetrical matrix P. Remember what P does? P transforms small vector r into large vector R. And now we're saying, what happens if we have a symmetrical matrix P? Then, with its two eigenvectors, x1 and x2, not just eigenvectors, x1 and x2, let's take the unit eigenvectors, x1 hat and x2 hat. This will have a component x1, y1. This will have a component x2, y2. And what we're doing is very similar now to what we did in video number 17. Here we have a matrix. Here we have the components of the eigenvectors of that matrix. That is what we call a model matrix in video number 17. So if we have that, then if we have this matrix, which is our matrix P, times this column, x1, y1, that's just going to be lambda 1 times that column, because this is an eigenvector, specifically a unit eigenvector now. Or this times this column, it's just going to be lambda 2 times that vector, that column vector. So if we have matrix, our matrix P, times a matrix comprised of its eigenvectors, and actually to be specific, we're using not just its eigenvectors, but its unit eigenvectors. If we multiply this out, that's the same thing as this matrix times this diagonal matrix, where the diagonal elements are the eigenvectors of our matrix P. And again, we discussed this at length in video number 17, but we can see why that's true. Again, multiplying this, that just simply gives us lambda 1 times this column vector plus lambda 2 times this column vector. Well, if we do this multiplication, it gives us the same thing. Lambda 1 times this column vector plus lambda 2 times this column vector. So this, we get this equation right here, just as we had done previously in video number 17. Now, something else to consider. The matrix that we formed by using the components of the unit eigenvectors, this matrix is an orthogonal matrix. We can see why. This column vector, it's a unit column vector, so is this one, and the eigenvectors, the unit eigenvectors, are orthogonal to one another. That's characteristic of an orthogonal, of a symmetric matrix. So these columns are orthonormal. So this is an orthogonal matrix. Now, this equation here is what we have right here. This is our matrix P, our symmetric matrix. Here's the matrix composed of its eigenvectors, actually its unit eigenvectors, and it equals this times this diagonal matrix, where the diagonal elements are the eigenvalues of this matrix. And again, we discussed that at length in video number 17. Well, if I multiply this matrix by its inverse, it's just going to give us the identity matrix. So if we multiply both sides of the equation by the inverse of this, well, what is the inverse of this? Well, again, these matrices are the same, of course. These are orthogonal matrices. And remember now, for an orthogonal matrix, its inverse is just its transpose. So this equation is the same as this equation. This is the transpose of this and is the inverse of it. So we have this times this. This time this inverse is just the identity matrix, gives us this. So here we have a matrix that is diagonalized. And again, it's the same as what we talked about in video number 17. We have a matrix and we have a model matrix comprised of its eigenvectors. In this case, it's unit eigenvectors. The difference here is that this is symmetric, so that these unit eigenvectors are orthogonal to one another. This is an orthogonal matrix, so its inverse is real easy to find. It's just its transpose. But we have this expression. Okay, now let's consider something further, though. Here, are the unit eigenvectors x1 and x2. And we said, of course, they have an x1, y1 component. This has an x2, y2 components to it. Now, notice here that if this is angle theta, then this angle right here has to be theta. Of course, this is a 90-degree angle. These are orthogonal to one another. So this angle going from here to here is 90 plus theta. Well, if this angle here is 180, then that has to be 90 minus theta, so that one has to be theta. Okay, but now we have two right triangles. In each case, the hypotenuse is 1. So x1 is just the cosine of theta. y1 is just the sine of theta. x2, that will be the sine of theta with a minus sign before it. We're going to the left. And y2 is just going to be the cosine of that angle theta. Okay, so let's now go back and again consider this equation, knowing what we now know about x1, y1, and x2, y2. Here we have that same equation right here. If we can get this into focus. There it is. Now, x1, y1, that is cosine theta, sine theta. And x2, y2, that is minus sine theta, cosine theta. But this hopefully looks familiar because this is this, same thing. So this is the matrix C. This matrix right here. We said earlier that here, we were talking about this type of system, that if we have axes that are perpendicular, then as we derived in video number 28, I believe it was, matrix C is this. And once again, now we're seeing that here, that we said that if matrix P is symmetrical, and these are the components of its unit eigenvectors, we had this equation, but now we see that x1, y1, x2, y2 is just the rotation matrix C. So what do we have? This was matrix P. That was this matrix here, a symmetrical matrix. So this is matrix P. This is matrix C. This is matrix C. And this is diagonal matrix, comprised of the eigenvalues of our matrix P. So we have this equation. Now, we multiply both sides by the inverse of C, and we have this equation. Okay, now let's go back to what we had earlier. We had this equation. Now, what we're saying here is that if, two things, if this is a symmetrical matrix and we use its two orthogonal vectors to form our x prime, y prime axis. Remember, we were saying, okay, matrix P has two orthogonal eigenvectors. Here they are, here and here. Well, this could be an x prime axis. That could be a y prime axis. If we do that, then when we derive this expression right here, this, we don't have to multiply three equations together. All we have is the diagonal matrix comprised of the eigenvectors of matrix P. So what we have then is that equals a very, very simple expression. And again, now if this is just an x prime, y prime system, here we have matrix P, and it is not symmetrical, it is non-singular, then we will have this similarity matrix that transforms an x prime, y prime point on small vector r into an x prime, y prime point on big vector r. On the other hand, if we have a different situation, this is a symmetrical matrix with two orthogonal eigenvectors, and its eigenvectors are used to form the x prime, y prime system, then this equation is just simply now, this is just a diagonal matrix. In this situation, as we just proven, is the diagonal matrix. Now we have a much, much simpler expression. So what we're trying to show is that you have a symmetrical matrix and you use its orthogonal vectors to form the x prime, y prime axis system, you get much simpler equations than if you did not use that, if you did not take advantage of that situation. And that's what's called the principal axis of transformation. And in the next video, we will have a specific demonstration with numbers. We'll work a problem like that. And then in the following videos, we will apply the principal axis of transformation to simplify quadratic matrices.